The successful installation of the bridge leaves at Herring Bridge in Great Yarmouth marked a significant milestone in a major civil engineering project undertaken by BAM Farran's joint venture for Norfolk County Council. The new bridge, which is scheduled to open in the summer of 2023, aims to enhance the local infrastructure by providing a vital link between key areas of the town and reducing traffic congestion. The installation process involved two massive bridge leaves, each measuring 45 meters in length and 24 meters in width. These substantial components, weighing 770 tons each, were fitted with an additional 500 tons of heavy concrete to serve as counterweights. This design ensures that when the leaves are raised, there will be a 50-meter-wide navigable channel between the two bascule chambers, allowing river traffic to pass through. The installation was carried out during a 72-hour river possession that began at 8 o'clock on the 21st of March. The first 24 hours were dedicated to positioning the east leaf in the closed position. Once the east leaf was in place, work shifted to the west leaf, which was installed during the subsequent period. By Thursday, March 23rd, both leaves were successfully raised to the open position, marking the completion of this crucial stage in the bridge's construction. The broader construction of the Herring Bridge project began in January 2021, starting with preparatory work such as setting up accommodation, enabling operations, and demolishing existing structures. This was followed by in-river marine works and the construction of approach embankments to support the bascule bridge and two underpasses. The comprehensive project also includes upgrading the local road network with a new 5-arm roundabout and a dual carriageway to facilitate smoother traffic flow. Once completed, the Herring Bridge will significantly improve connectivity by linking the A47 at Harfreys Roundabout to the Port and Enterprise Zone across the river. This enhanced connection is expected to alleviate traffic congestion in Great Yarmouth, resulting in shorter and more reliable journey times for commuters and freight. The bridge's construction is not only a feat of engineering, but also a strategic development to boost the local economy by supporting investment, regeneration, and economic growth in the town and the wider borough. The replacement of Dickinson's Creek Bridge, completed in May 2015, marked a significant infrastructure improvement in the region. Located in a crucial area, the original bridge served as a vital link for local transportation, facilitating the movement of goods and people. Over the years, however, the bridge had deteriorated due to age, increasing traffic demands, and exposure to environmental elements. The decision to replace the bridge was driven by the need to enhance safety, increase load capacity, and extend the lifespan of the structure, thereby ensuring its ability to serve the community effectively for many years to come. Dickinson's Creek Bridge, originally constructed decades earlier, had reached the end of its serviceable life. The existing bridge had become structurally deficient, with visible signs of wear, such as cracks, corrosion, and weakening support structures. Inspections had revealed that the bridge no longer met modern safety standards and was struggling to accommodate the increased traffic volume and heavier vehicles typical of contemporary use. Given its strategic location as a key route for local traffic, including commuters, commercial vehicles, and emergency services, the decision to replace the bridge rather than simply repair it was deemed necessary. The old bridge's limitations posed several risks. Its narrow width, combined with deteriorating guardrails and a weight limit that restricted certain vehicles, made it increasingly challenging to ensure safe passage. In the case of heavy rains or flooding, Dickinson's Creek was prone to rising water levels, which placed additional stress on the structure. This made the need for a more resilient bridge that could withstand natural forces and support the community's growth even more urgent. Planning for the replacement of Dickinson's Creek Bridge began with an assessment of the site, traffic requirements, and environmental considerations. Local authorities, engineers, and environmental consultants collaborated to design a new bridge that would address the deficiencies of the old structure while minimizing disruption to the natural surroundings. The design incorporated a wider deck to accommodate 2 lanes of traffic, safer guardrails, and a higher load-bearing capacity. Additionally, the bridge's elevation was increased to reduce the risk of flooding and to improve the hydraulic flow of Dickinson's Creek. Sustainability was a key factor during the planning stage. The new bridge design took into account potential environmental impacts on the creek's ecosystem. Efforts were made to minimize the disturbance to local wildlife, vegetation, and water quality during construction. Measures such as erosion control, proper waste management, and temporary structures to reroute water flow were implemented to protect the natural habitat. The construction of the new Dickinson's Creek Bridge began in early 2014, with a targeted completion date set for mid-2015. The project involved the demolition of the old bridge, which was carried out in stages to ensure minimal disruption to traffic. Temporary detours and alternative routes were established to accommodate the continued flow of vehicles while construction was underway. The new bridge was constructed using modern materials and techniques to ensure durability and longevity. High-strength concrete and weather-resistant steel were chosen for their ability to withstand harsh environmental conditions, such as freeze-thaw cycles and flooding. The construction also included new piers and abutments designed to provide better support and stability. The use of pre-cast components helped to speed up the construction process, reducing the time spent on-site and minimizing inconvenience to the public. By May 2015, the new bridge was completed, meeting all safety and quality standards. The project was completed on schedule and within budget, a testament to the meticulous planning and efficient execution by the construction team. The replacement of Dickinson's Creek Bridge brought numerous benefits to the community and the surrounding area. The new structure provides a safer and more reliable crossing for motorists, cyclists, and pedestrians. Its wider deck and improved load capacity accommodate modern traffic demands, including larger commercial vehicles, thus facilitating economic activities. The elevated design helps to mitigate the risks associated with flooding, providing better protection for the bridge and nearby properties during periods of heavy rainfall. The enhanced durability of the materials used in construction ensures a longer lifespan for the bridge, reducing the need for frequent maintenance and associated costs. Furthermore, the project demonstrated a commitment to sustainable infrastructure development by incorporating measures to protect the creek's ecosystem during construction. The new bridge, therefore, represents a blend of functionality, safety, and environmental responsibility. Over the Easter weekend of 2018, Iron Rod Éireann Irish Rail, in collaboration with contractor Sisk, successfully installed a new underbridge on the main Cork-Dublin rail line at Osborstown near Sallins for Kildare County Council. This project, completed in a tight time frame, represents an example of modern engineering and logistics prowess. By minimizing rail disruption and completing the work in one weekend, the installation achieved its objective of enhancing the local road infrastructure while ensuring minimal inconvenience for rail passengers. The newly installed underbridge is a crucial component of a broader infrastructure initiative aimed at improving the region's transport network. The project will facilitate a road bypass under the existing rail line, enhancing connectivity for road users while maintaining the efficient operation of one of Ireland's busiest rail corridors. The installation is a significant step towards alleviating traffic congestion in the area, making travel safer and more convenient for local residents and businesses. The installation of the underbridge was the result of extensive planning and preparation over several months. The bridge's itself was pre-constructed in sections beside the railway line to allow for quick assembly during the Easter weekend. This preparatory work was crucial in ensuring the project could be completed within the narrow window allotted for the installation. The sections were fabricated off-site and transported to the installation location, where contractors Sisk and Iron Rod Aaron worked in coordination to assemble the components and prepare the bridge for placement. Work commenced early on Good Friday, with crews starting at 0:30 hours. The rail line was closed to all train traffic, enabling workers to carry out the tasks without disruption. Heavy machinery was brought in, including cranes capable of lifting the large pre-constructed sections into place. The use of prefabricated components was a key strategy in reducing the time required for installation. By doing as much work as possible in advance, the contractors minimized the risk of delays and ensured that train services could resume promptly. The actual process of installing the underbridge involved several critical steps that were carried out in a highly coordinated manner to meet the tight schedule. After the railway line was closed and the initial site preparation was completed, the old track bed had to be excavated. This excavation created space for the placement of the new underbridge while ensuring that the foundation was adequately prepared to support the weight and dynamic loads of the rail traffic. With the excavation completed, the pre-constructed sections of the underbridge were then lifted into position using cranes. Each section had to be aligned precisely to ensure structural integrity and fit seamlessly together. This task required meticulous planning and precise execution, as any deviation could have resulted in significant delays or structural issues. Once the bridge sections were in place, the surrounding area was backfilled to secure the structure, and new track ballast was laid. Track reinstatement followed, involving the careful replacement of the rail track over the newly installed underbridge. Workers had to ensure that the track alignment and gauge met strict standards, as any imperfections could affect train operations. The final stages included testing the rail track and signaling systems to guarantee that everything was functioning correctly. Completion and resumption of train services. The entire process, from the closure of the rail line on Good Friday to the reinstatement of the track, took approximately 82 hours. By 10 o'clock hours on Easter Monday, the track was fully restored, allowing for the safe resumption of rail services by 12:30 hours that day. The efficient execution of this project not only met the planned schedule, but also set a benchmark for future infrastructure works of this nature. This rapid completion was particularly important because the Cork-Dublin rail line is one of Ireland's busiest, serving thousands of passengers daily. Minimizing disruption was a priority, and the team's ability to restore services within the targeted timeframe ensured that passengers experienced minimal inconvenience. The successful installation of the underbridge demonstrated the effectiveness of modern construction techniques and project management strategies, including the use of prefabrication and around-the-clock work schedules. The new underbridge is expected to bring significant long-term benefits to the area. By enabling a road bypass beneath the railway line, the structure will help reduce traffic congestion in and around Osborstown and Sallins. This is particularly important for the local community and commuters, as it will ease travel times and improve road safety. The bypass will also facilitate better connectivity for businesses in the region, potentially boosting local economic activity. From a rail infrastructure perspective, the installation of the underbridge enhances the safety and efficiency of the railway. By allowing for an uninterrupted road crossing underneath the rail line, the project eliminates the need for level crossings in the area, which are traditionally associated with safety risks and potential delays. Steel construction and engineering involve a comprehensive and collaborative process that transforms raw materials into complex, durable structures. It begins with a deep understanding of steel's properties, strength, versatility, and sustainability, making it an ideal choice for a variety of construction projects. The process combines craftsmanship, cutting-edge technology, and meticulous planning to meet the high standards required in modern construction. The initial phase focuses on design and engineering, where detailed plans are developed to meet specific structural requirements. Advancements in design techniques, computer-aided design, CAD, and 3D modeling allow for more sophisticated and efficient structures. Once the design is finalized, high-quality steel is selected based on the project's specific needs, such as strength and weight requirements. The steel is then fabricated into various components in specialized facilities. This fabrication involves cutting, shaping, and welding the steel into beams, columns, and other structural elements, with precision being essential to ensure that each component fits perfectly during assembly. During the construction phase, prefabricated steel components are transported to the site and assembled. This process requires skilled labor and specialized equipment to safely lift and position large steel elements. Efficient project management and logistics are crucial, as steel construction often involves assembling structures in challenging environments, such as high elevations or confined spaces. Throughout the construction process, strict quality control measures are implemented to ensure that all elements meet design specifications and safety standards. This includes inspecting welds, connections, and the overall integrity of the steel structure. Working with steel demands high safety standards due to the potential risks involved in handling heavy materials and working at heights. Modern steel construction also places a strong emphasis on sustainability. Using lighter and more durable materials reduces the environmental impact, while efficient designs minimize waste. After construction, regular maintenance ensures the longevity and safety of the structure. Marine pile driving is a crucial process in marine construction, which involves installing piles, long, slender columns made of steel, concrete, or wood, into the seabed to provide structural support for various marine structures, such as piers, jetties, bridges, and offshore platforms. The procedure helps secure these structures against the dynamic marine environment, including waves, tides, and currents. Marine pile driving requires specialized equipment and techniques to address the challenges posed by underwater conditions and varying seabed compositions. The vibratory hammer is a primary tool used in marine pile driving. In this case, a TUNKERS 60.2 HVB vibratory hammer is utilized, which is a specialized hydraulic tool designed for driving piles into the seabed. The vibratory hammer works by generating high-frequency vibrations that loosen the soil and reduce the friction between the pile and the surrounding material, making it easier to drive the pile into place. Vibratory hammers are especially effective in granular soils such as sand and gravel, but can also be used in other seabed materials like coral with some limitations. To power the vibratory hammer, a hydraulic power pack is employed. Specifically, the TUNKERS hydraulic power pack. This power source provides the necessary hydraulic pressure to operate the vibratory hammer, ensuring that the pile driving process can be carried out efficiently. The power pack's capacity and reliability are crucial in maintaining the continuous operation needed to drive the piles to the desired depth. Before the pile driving process begins, soil testing is conducted. Soil test number 1 mentioned in the document serves to assess the seabed composition and determine the best approach for pile installation. Soil tests are vital for understanding the properties of the seabed materials, such as their density and load-bearing capacity, which can significantly influence the equipment choice and driving technique. In this case, the piles are driven into solid coral, a challenging material that requires appropriate preparation and equipment to ensure successful installation. The process also involves setting up a template installation, which is a frame or guide used to ensure the accurate placement and alignment of the piles during installation. The template holds the piles in the correct position and orientation as they are driven into the seabed, minimizing deviations and ensuring structural integrity. The driving process begins with pile number 1, which measures 36 feet in length. The pile is driven to a depth of 28 feet at the tip, reaching solid coral. Driving piles into coral can be challenging due to its hardness and density, necessitating careful control of the hammer's energy and driving speed to avoid damaging the pile or the hammer.